or problem 9. My answer key is an old version of the worksheet, and it looks like I used to have a different problem in here that I've taken out. So my numbers are off a little bit on my answer key, so sorry if I keep referring to the wrong numbers. The next problem, we are looking to diagonalize the matrix 4, 3, negative 3, 4. Let's see if we remember how to do that. So the first thing that you need to do is find the eigenvalues. The eigenvalues are going to give us the diagonal matrix D. And this is a problem that we did back earlier in the packet. For me, it's number 4. Hopefully it's also number 4 for you. But we did this earlier. We found that the eigenvalues were going to be 4 plus or minus 3i. And what we learned on the last 2 problems is if you find one of the eigenvectors, you will be able to take its conjugate, and that'll be the other eigenvector. So using 4 plus 3i, pause this video, try to find the eigenvalues, try to find the eigenvector that is associated with that eigenvalue, and we will check your answer and go from there. You should get an eigenvector of negative I1. If you did, you can skip ahead on this video a little bit. If you didn't, I'll explain it. So if I find my vector v minus lambda I, so I'm going to have 4 minus 4 plus 3i. The 4's reduce out, just giving me a negative 3i. 3, negative 3, and then the same thing happens here, negative 3i. And, oh, sorry, what am I doing? I am getting myself confused. Let's try that again. Oop, 0, 0. So I am reducing this matrix. Well, no, I'm not reducing it. I'm just looking for its solution. So if I take that second line, negative 3x1 minus 3ix2, negative 3x1 equals 3ix2. x1 is negative ix2. So if x1 is negative ix2 and x2 is x2, that's going to give us the vector negative I1. So now we know if the first vector is negative I1, then that means for lambda 2, its vector is going to be positive I1, which is nice. And the diagonalization, so we're looking for P and D. So D is going to be composed of my eigenvalues. And then P is going to be the eigenvectors. So negative I1 and then I1. Okay, so with this part, the last part of this problem, verify your answer by comparing VP and PD. The key is that we should get the same thing. If we multiply V, which was the original, times P, and then P times D, we should get that VP equals PD. So that is a way to check. You can do that on your own. The result, we should get the same thing. We do get the same thing, and you can check on your own, but that's the one way to check these, is that multiplying the original matrix V times P, we should get the same thing if we just take D times P, or sorry, P times D in that order. So the last part is just an explanation, and I talked about this earlier in the video. So we have things that occur in complex pairs. So the eigenvalues occur in conjugate pairs, the eigenvectors occur in conjugate pairs, which is nice, especially with the eigenvectors. It means you just have to find one, and that'll tell you what the other one's going to be without having to go through all the steps. I hope this video made sense to you. We are going to move on into the 5-5 notes part 2. And that is not as long, but it does go through the kind of the main application of using these types of matrices. So that's it for this video, and yeah, I'll talk to you later.